This last part, I just want to go through some examples of the math of calculating a z-test and how we're actually visualizing whether it's significant or not. So my example here is it is expected that male American students are lonelier than male students in general. So we have a sample male students mean of 38.74 on a scale of loneliness, the standard deviation of 9.30, and that is our worldwide. So we know that male students across the board from a previous example have a mean of 38.74 and a standard deviation of 9.3. We take a sample of 40 male American students that we actually measure, and on the same scale find they have a mean of 37.06 and a standard deviation of 10.91. So again, thinking about what we need to know the overall mean. We have that, 38.74. The overall standard deviation of the population, we have that, 9.30. We need the mean of our sample, which is 37.06, and we need to know how many people are in our sample, and it needs to be over 30. We have 40, we're good. So our assumptions are met, and we'll assume that this is normally distributed data. So again, we have our male students in our population of 38.74 mean, standard deviation 9.3. We have our sample of 40 and a mean of 37.06. So we're just going to plug this information in. Now, the first thing we need to do is calculate that bottom of the equation. So remember, we're going to take the standard deviation of the population, sigma, 9.30, divided by the square root of our n, 40. So again, we're going to use our scientific calculators, take 9.30 divided by the square root of 40, and we get 1.47. So that's the bottom of our equation. So the top of our equation is simply our sample's mean minus the population's mean. So in this case, 37.06 minus 38.47 or 74, which equals negative 1.14. And we're going to divide that by the bottom, which we've already calculated, 1.47. Again, this is a one-tailed test, so we had a directional. We expect that our sample is actually going to be sadder or more lonely. So we have a one-tailed test. So our critical value is 1.645. That's what we need to be able to claim statistical significance. So we get a z of negative 1.14. That's what we actually get when we take the mean of our population, our sample, divided by our mean of our, minus our mean of our population, and divide by, again, that sigma of our mean. So in this case, it is not significant. On average, American students are about as lonely as male students. In other words, we have to reject our hypothesis. Now notice that that doesn't mean that there isn't a practical difference. We did get a lower score. But what that tells us is that we aren't confident enough in that score for us to make a causal or a relationship statement. So when we say non-significant, it doesn't mean that it has no value or no meaning. It means that we had to reject it based on this high bar, that the probability of us being correct is not high enough for us to be confident. So again, remember that what we're doing is we're comparing our samples distribution to this probability distribution. And the probability distribution in this case with the z-score for single samples doesn't change. If we have a one-tailed test, our critical value is 1.645. That is our bar, if you will, that we're trying to make. And what we're going to do is we're going to compare our actual sample distribution. So again, we have our probability distribution, we have our critical value, and then we have our sample distribution. If our sample's distribution is significantly above, in other words, the difference we find is on average above the critical value, then we can claim it statistically significant. If it is not, we have to claim it is not statistically significant. So is a sample mean significantly different than the population mean? Again, we have our actual mathematical equation, and to write that out, it's the sample mean minus the population mean divided by the standard error of the population mean. And again, the two critical values to keep in mind is that if it's a directional test, that value, once that obtained test statistic, needs to be above a positive or negative 1.645. Or if it's a non-directional hypothesis, it needs to be above positive or negative 1.960. And again, remember the bottom of that equation is here. The sigma represents the standard deviation of the population, so the known value, divided by our samples in the square root of. And again, what that represents in words is the population standard deviation divided by the number in the study, the square root of. So the main point, statistical significance for Z for single samples indicates whether a sample differs from a population mean and how likely that difference is due to chance. In other words, the statistical significance isn't about the difference, it's about the probability that the difference occurred due to there being a systematic difference and not random chance. When interpreting test statistics, always consider whether it's statistically significant. If it is statistically significant, make sure that you are talking about the direction of the difference, so which group scored higher, and the size of the effect. So statistical significance does not reflect how meaningful the difference is. And we'll be talking about effect sizes moving forward as well. So the larger the difference, the more practical that difference is. And again, inferential statistics are used to infer the results based on a sample to a population. We compare the obtained test statistic to a population's test statistic probability distribution and looking to see is the obtained test statistic higher than the critical test value. Z-test is an inferential statistic comparing a single sample to a population when the variance of the population, mean and standard deviation, is known, and our sample is above 30.